Good afternoon, everyone, and welcome to this second video of the ninth week of CS470 Advanced Computer Architecture. We're going to do two things today, relatively independent one from the other. One is to have a look, relatively superficial, but a brief look to the polyhedral model. You'll see what it is, but it's all about rearranging, optimizing loop constructs in such a way as to achieve better performances. The second part connects back to the first video for today, that is the video of last week that was partly overflowing into the lecture of today. Going back to the discussion on high-level synthesis and discussing a few further limitations of high-level synthesis and high-level synthesis techniques as we know them as of today, and seeing what, as a designer, as a architect, we can do to improve performance in pretty realistic cases. The first thing that we are going to do today is to look at this polyhedral model for loop optimizations. The problem is a problem that we have been knowing for some time, that we probably visited the first time when we were talking of VLIW compilations. And the idea is that you can rewrite, and sometimes it's useful to rewrite loops in different ways. For instance, split different parts of an iteration into different loops, or the opposite, merge two loops together, or do some of the transformation, for instance, also exchange the order of the iterators. If you have nested loops, exchange the order of the outer and inner iterators so that you do the iterations in a different order. Typically, the reason for doing this is that you want to reduce or maybe more create more distance, temporal distance between dependencies, so that you can build better schedules. The same problem actually occurs, maybe we evoked it in last week, in high-level synthesis, because most of the high-level synthesis, at least the statically scheduled high-level synthesis, is essentially the same problem, is essentially the problem of elaborating a schedule at compile time for a sort of VLIW processor that doesn't exist and that we construct on the fly for a given application. The problem that we have not looked at is how to express these optimization, how to perform these optimizations. It's great to say I can split or I can put together the loops, but if I have to write an optimization problem, a formal algorithm of optimization based on how I transform the loop, I need to describe formally the transformations that I could potentially do on the loop. And this is one thing that one can do pretty conveniently with the polyhedral model. And so I want to give you a glimpse of how it works. It will not be a very deep or comprehensive treatment of the polyhedral model. It's actually a very complex topic, but really I want to give you a glimpse, a sense of how these things go and what is the potential that is there. Because of the superficiality maybe of what we are going to do on the polyhedral model, this is probably not going to appear in the exam. I hope you are still there. I suppose that saying this makes most of the people close the video. No, jokes aside, let's go. So the problem is describing, right? It's describing the program execution, understanding the fact that there are iterations, multiple iterations, so that have succeed that are executed successively for a number of times, the understanding of what is the execution order across these iterations, and especially everything that we really care is about the memory accesses, the sequence of memory accesses, because we'll come back to this a little later, but essentially this is what, provided we do the different operations, we need to we can reorder them arbitrarily, except for the fact that we need to obey the dependencies that exist in the executed code. So we need to express all these things in some formal way so that we can make modifications and verify on one side that we have not made anything illegal, and on the other side express an optimization problem, a formal optimization problem that can be used to find a solution that is better than what we start. So this is exactly what the polyhedral representation is useful for. And what it can do is something that unfortunately is quite restrictive, quite limited. So it can we can use it to describe what are called static control parts and loops made of static control parts, which are regions in which all control flow decisions and memory accesses are known at compile time. And the loops must have all their expressions in the induction variables, so whatever are the indices of the memory accesses along all the dimensions of matrices or vectors that we access, all these things must be affine expressions. So it is something extremely constraining, if you want. It brings down, compared to the programs that we write, brings us down to an extremely small space, but it is an important space. For instance, typically digital signal processing applications, or at least many digital signal processing applications, do fit this this kind of definition and this kind of restrictive limitation. Once more, this is not surprising, right? The reason why VLIW processors and maybe static high-level synthesis tend to be successful on signal processing application is partly linked to this fact that these programs are sufficiently well-behaved, these applications are sufficiently well-behaved, that techniques like this one can be applied to achieve very powerful optimizations. Here you have three examples of what are scopes, so that are programs that where the polyhedral representation can be applied. Maybe more interesting is to start seeing cases that fall out of that, right? For instance, if you have incrementation or changes of the induction variable, the loop increment, that are not affine, you are out of this. So if you are doing a square of the previous value of the induction variable or anything non-affine, you are lost. I suppose that everybody understands the word affine, but maybe not. So affine essentially means a linear function of the induction variable plus constants, right? Plus a translation, right? So as soon as you do a square, of course, this is not linear and doesn't work. The second example that we see in the middle of the slide is the fact that you have an indirect memory access. So as soon as you have an indirect memory access, you are not, you cannot understand the memory accesses at compile time, because it's data dependent. It depends from the B of I, which element of A I am accessing, so nothing can be done anymore. And again, this gives you a sense of how limited this kind of techniques are, right? A lot of programs that we do have pointers. If we are doing programs about graphs instead of about manipulating samples coming from some whatever signal, well, in a graph, we certainly have all the time pointers, and we have accesses that are therefore determined by the content, the data values, and all these falls apart. It's just not usable. The third example is another pretty natural example for our programs, and again gives us a sense of how restricted the use of these techniques is. For instance, the fact that we are making a test on a of I, which is a piece of data that we don't know, and therefore the control flow is not cannot be understood, anticipated at compile time. It depends from the data that we have. So if we are not in these cases, and again, it's relatively, if you want, unlikely that we are within, but if we are within, and there are applications that are within, we can do a number of things. And these are the kind of things that we can do. The first thing is that we can model the iteration domain. Basically, what are the bounds of our induction variables, right? And what is interesting for the way this mechanism goes is to express them not so much through independent inequalities, but essentially express them in ways that are like what you see here, which is relatively easy to see, but everything so is in the form of matrices and linear algebra, where you have here an augmented vector with all your iterators ij and the constant 1, and here a number of constants. Is relatively easy to convince yourself that what this says when you are comparing it with the null vector is essentially the same thing that is written here. And actually this way of writing can be used for any possible form of scopes of these types of programs. You can always write in a way like this: what are the bounds of the iterations? What are all the iterations that you are going to do on of this in this program? Once you have a sense of what are the bounds, what are the all the iterations that you need to do, there is a need to describe the schedule. There is a need to describe formally what is the which iteration is before another iteration. And of course, depending on how I write my code, it doesn't mean necessarily that what is a smaller iterator, iterator I equal to 1, will come before iterator I equal to 3, right? Because of course I could be writing the exact opposite that goes from n to 0, for instance, right? The nice property is that when you have these affine functions in all the program, everywhere where you use your induction variables, you can write matrices like this phi that take your iterators ij, your vector of the iterators, and the multiplication of this phi that depends on the program captures essentially the sequence of accesses that are done by the program. This is the matrix that corresponds to this two loops, and this the way these two loops evolve, gives you a vector. The product of the ij times this matrix gives you a vector, and this vector is guaranteed to be in lexicographic order during the execution. In other words, once you multiply by the characteristic matrix of this of the specific program that you have, the iterators, you obtain something that is guaranteed to be in lexicographic order, and therefore you can check if two iterations, two real iterations that are here, are in the correct order that should have been by multiplying by the matrix and comparing the two vectors. Lexicographic order means that a vector is before another if the first element is smaller, or if the first element is equal and the second element is smaller, or the first two elements are equal and the third element is smaller, and so on and so forth, right? So through the lexicographic order of the product of this characteristic matrix by the iteration that you are at, you can tell which iteration comes before the other. So this is a trivial case in this case because you have the characteristic matrix that it is an identity matrix, but you see here a few more examples. For instance, here the internal loop is reversed, and if you take two iterations like 1, 3 and 1, 6, so two pairs of values of ij 1, 3 and 1, 6, and you do understand before even looking at the math that this one is before this one. Why? Because j is decremented, so a larger j for the same I comes before a smaller j, right? You see it here. And now if you multiply this 1, 3 or 1, 6 by this characteristic matrix, you get 1 minus 3 and 1 minus 6, which are in the correct lexicographic order. That is, this one comes before the other one, and that is the 1, 6 executes which generated this value, comes before the 1, 3 that generated this value. So again, what you are doing is that you have now you can develop, and now I'm not even telling you how to do it, but you can develop and you have a guarantee that you can write this matrix, and this matrix will tell you in which order a couple of iterator, a vector of iterator, in which order the corresponding iterations will have to be done, right, or were done by the program. Again, you are describing the program and you are describing how they sequence through this matrix, which is an extremely compact way to describe it. And it can be so compact because, in fact, what we have said is that we have restricted hugely the type of programs that we can describe. The other thing that you need to describe are the memory accesses, right? Which accesses you are going to do within which part of the memory. So, for instance, what you can do is that you can tell, you can create an image, or you can measure the image of what are all the values that are going to be accessed during the execution of all the iterations of the problem. And you can obtain this easily from the access pattern and from the iteration domain. What are all the iterations that you are going to do, again, because everything is statically anticipable, so it's relatively easy to compute. And so once you start describing what is your program, and I want to insist on one thing, right? Essentially, what you have here is a synthetic description, very much implicit, very much non-intuitive. If you look at it just like this, it's just a matrix, but it is an intrinsic description of the sequence of iterations that you have to do. It doesn't matter what the iteration is, right? I'm not putting it here. It's some computation, but this computation is done for a number of times, and this tells me essentially everything about the sequence of these iterations. And now we can start thinking of transformation, that is saying, okay, now I have these iterations, maybe I want to do them, but I want to do in a different order. I want to do some fusion, right? And you remember fusion, I think we used exactly the same term, right? Is I have two loops, so I have two different bodies, and maybe they are done in they have the same iterators, so I am doing all the iterations for one body, and then I do all the iterations for the other body. Maybe I could fuse them, which means that I do iteration 0 for one body, iteration 0 for the second body, iteration 1 for one body, iteration 2 for the other, iteration 1 for the other body, and so on and so forth, right? I'm interspersing the iterations. So I'm changing, it's a schedule transformation. It's a transformation that changes the order of execution of the bodies. The bodies are the same, so somehow that amounts to the same. But I change the way I do. So here you see the classic things, again, fusion, distribution, which is the opposite. Some people call it fission, and maybe we call it fission when we were talking of VLIWs and so on. And these are modification on the schedule. That is modification on this matrix that we have been discussing a couple of slides before. And one of the key issues is, okay, I can transform the schedule, I can change the loop bounds, the order I do the different iterations, but what makes my transformation legal? And the answer is relatively simple, right? Provided I'm doing the same operations overall, that is, in the end, I execute the same number of iterations, the same operation for each iteration, I can exchange them as I want, I can reorder as I want, provided that all the dependencies, and all the dependencies through memory in particular, are preserved, right? It's always the same story. It's what we have been doing for the last 10 weeks, right? We have been trying to reorder things as aggressively as we can, but we have a constraint, which is dependencies need to be obeyed. And what I think you can imagine, although I'm not going to show you real examples because they are a little bit difficult to fabricate, but I think you can have easily the idea that through this formalization that gives me from any vector of my iterations, gives me vectors that have to be in a specific order that represent the order of execution of my actual code. I can use this to go and verify that if it was in a specific order 2 accesses before the transformation, well, the same order has to be in after the transformation. And I put these as constraints that I can use in formalizations like ILP or SAT or whatever tool you want to use for doing your optimization, where these are constraints that cannot be violated, and then you formulate around this optimization problem. So here are some examples, more maybe, if you want, qualitative than quantitative, or just sort of, they are individual examples. They are not a formulation of an optimization problem per se, but it's just to give you a sense of how you can use these phi's to express modifications to the schedule. Here we have a piece of code where we have three loops in I, J, and K, where we initialize one matrix in the second innermost loop, and in the innermost loop we compute something and we overwrite the initialization, or we keep overwriting, right? You see very well that this is a simple, what is it? A matrix multiplication, right? So it's a simple typical program. And you can describe them in the way that we have done before them through these phi matrices. Actually, these are slightly augmented because we augmented the vectors, the ijk iteration vectors of this instruction or this statement and of this statement with a constant n that appears in the program and with 1. And what is the power or what is the interest of this representation? The interest of this representation is that we can use these matrices to show, to express transformations of the code without doing the transformations on the code or without thinking of code, really. For instance, if we add a 1 here, right? What it's going to say is that if I do the product between this matrix and this vector, what it tells me is that the top element is I plus n, then j, and then k, and which means that it translates the sequence of these ijk n essentially after all the iterations of this, which corresponds to what you see here, right? Instead of having these two S1 and S2 that happens all the S2 after the corresponding S1, because this is the third loop is inside the second nested loop, the J loop. Now the K loop happens by redoing afterwards the I and J. You see it here. So I has been translated by N, has been moved N after. So it's completely after all these iterations, and which corresponds to a loop distribution or a loop splitting, however you want to call, right? So we have here the first part of the loop, this S1 that is done in a first loop, and then virtually the same loop that is done again afterwards, where there is the second part of the body, which was the iterator of K and the statement 2, which appears here, right? And if you want, this n is only cosmetic because I could take away this n from here and it would be the same thing. But the way I added this n here, right? This 1 multiplies by n, and I'm adding n to I. That's what is happening here. Is a way to express that all these iterations will happen after all the iterations of S1. So exactly the loop distribution. So this is the idea, right? The idea is that by manipulating the sort of these linear algebra objects that I have here, I get to represent different shapes of code, right? This code is very difficult to imagine how to have a good representation of this code with respect to this code and compare the correctness of one compared to the other. And this is exactly what this polyhedral representation gives us. Is a very compact way to modify things. Here is a second example that on top of having added this 1, I have changed it. Instead of having 1, 1, 1 here, I have 1, 1, 1 in a counter diagonal of this 3 by 3 first matrix that then is augmented with 2 more columns. What is this going to do? Again, do this multiplication, right? You multiply this by this. If you remember before, we had the result of the multiplication was I plus n j k, and now what we get is k plus n j I, right? I multiplies by 1, so here I have I, j multiplies by 1, I have I, k multiplies by 1, I have k here, plus n multiplies by 1, here, right? So what I have is that now I have inverted and reversed the 3 loops for uh, the second loop. So I have still the same distribution because of the n that I have added here. And on top of that, I have interchanged the order of these nested loops. They are kji instead of ijk. I'm not saying anything about whether it is useful or not. What is important is that by manipulating these matrices, I'm expressing changes to the code. I'm also not saying that they are legal, right? For instance, I could do something like this, where I shift by n this first loop, right? It's the same thing that I was doing before here. I went back to the original matrices, right? No, actually, I still have this one inverted in order, but I added the n here instead of adding the n here. Now, what this n added to the first coordinate means is that all these iterations will now be after, so all the iteration of S1 will be after the iteration of S2, which is what is written in code here. Again, there is an immediate correspondence between the code and these matrices. So the code that corresponds to this modification is here, which is essentially the same code that we had in the previous slide, except that the additional n over I is no longer here. Actually, it was over k in the previous slide, but now it's here on the I of the statement 1. And all these statement 1s are happening after the statement 2. Now, this is an example of something that is illegal, right? Because I'm initializing the matrix and then I'm adding to this initialization to 0 something, and now I'm first adding something and then initializing to 0, which is a write after write violation for the same corresponding elements, which makes all my program completely nonsensical and therefore wrong, right? Again, what is the purpose of this? The purpose is that I can express correct and incorrect schedule modifications, but I can use these modifications, this transformation, both to measure what is the potential impact on my scheduling ability. When I have a new schedule, I can check whether I can do a better job or I can do a worse job. And I can also use this to check whether there are violations, because I can use the fact that there is a write after write dependency between S1 and S2, and I have to check that all the S1s happen before the S2, which again, through this representation, I can verify. And I can verify that all these happen before these, which is clearly violated here, and therefore this is one possible solution, but is a bad solution because it's not semantically correct. Okay, so I hope this gives you a bit of a sense of the fact that there is this formalism that helps us to describe programs in a very compact form so that we can write optimization problems over them. And here is an example of something that one can do that is really not trivial with this kind of representation. Here is a real denoising application, classic signal processing, where you have these two loops that you have to do with a number of dependencies. There are no dependencies here, but there are some dependencies at this level. And these dependencies are such that you have this, right? You have, whenever you are increasing J, you are going to the next iteration in J, you are dependent, this arrow indicates dependency, you are dependent on the previous iterations, right? And the same is true on the I iteration. So you can turn trivially all the iterators around, but you still have a dependency between neighboring iterations. And since this dependency is between neighboring iterations, this is going to limit your initiation interval. You cannot initiate quick enough a new iteration because you need to be finished with the previous one not to violate this dependency. And what you can do by applying this kind of techniques with this tool, what it allows you is to uh, change the shape of this dependency, essentially redefine new variables that are slanted in a specific way. You can look, of course, the part that you will understand more easily is the code itself, but you see that is not at all self-evident to tell that this thing is the same as this one in terms of computational result. But the advantage is that what you have done is that you have skewed uh, this matrix in this way. And what happens now is that when you go from J1 to the next J1, right, this J prime, if you want, this changed new J, new iterator, when you go from one to the next, in the iteration, you do not have a dependency anymore. Now, the dependency is between these diagonal elements, which are more far away in the computation. And since they are more far away, they will help achieve a smaller initiation interval, and therefore an overall improvement in execution. And you see here a number taken from some paper that applies these techniques, where you start with a program that the best you can do is 5,000 cycles, and you reduce it by 20 times by applying automatically these techniques. So they are techniques that are incredibly interesting, not at all easy to apply. There are tools actually available that can help you doing this, connected to compilers and so on. They are incredibly powerful in those cases where you have some properties in your code that are true. They are very stringent properties, but there are still a number of programs that fall within the boundaries of these properties. And in those cases, you can formulate optimization problems that make both your VLIW programs much more efficient, and that is useful for VLIW applications in signal processing inside your cell phone, maybe. And they allow you to find very non-intuitive solutions for instance, high-level synthesis and design of accelerators. Unfortunately, they are not applicable in fairly general programming tasks where you have irregular behavior, you have memory accesses that are not statically determinable, which are most of them when we do our typical programs, when you have variable latencies like caches that can miss, when you have tests that are data dependencies that, once more, it's pretty common, right? And so we are left with the question of what to do with the rest, but at least we have a tool that allows us in that restrictive domain to make, in some cases, even optimal decisions. In this second part, we're going to look at some of the difficulties that we are likely to encounter the moment we try to convert a program that is an executable specification of a specific application into a high-performance digital circuit. We look at it from the perspective of high-level synthesis, but we'll also look at it from the perspective of whatever I can do, even if a high-level synthesis cannot do it. Why is this important today? Well, it is extremely important because, as we all know, we may be facing a time where transistors will not get cheaper, transistors will not get significantly faster, and in a sense is potentially a world where architecture is all that matters. Creating circuits better is the only opportunity that we have in the future, maybe, to increase significantly the performance of our computing systems. So we look at the perspective of creating accelerators and taking these pieces of code and creating circuits. And one of the difficulties, one of the basic difficulties initially is the handling variable latency, right? And variable latency is a bit all over the place. We'll come to some more complex examples later, but the classic things are units that may have different latencies for different operations or for different operands, or things as trivial as memory hierarchies, right? We know extremely well, because it's the bread and butter of architecture, that we have caches, and caches may hit or miss. And having circuits that don't understand this from a computational perspective may be extremely problematic. And the problem starts from the fact that if we do extremely simple circuits that are statically scheduled, like most of the HLS tools are able to do, the first most natural way to go about this is to assume worst case latency, which in the case of caches essentially means assuming that everything is a miss. In other words, making caches perfectly useless. We're going to use in all this part of the lecture of today this example. I think you can stop the video to try to study it a little bit more in detail. It's not important actually to understand exactly what it is and how it works. It is a sparse matrix dense vector multiplication. So it's a sort of classic computational kernel, but it's good for us because it contains a bit all the ingredients that might be difficult to handle. So again, you can stop the video maybe to read it with more comfort, but essentially what we do is that you go through a number of rows in the matrix. For each matrix, you have pointers in one data structure that tell you where is the start and the end element of the row. It's sparse, so you don't know how many there are, right? That are non-null. The idea of a sparse matrix is that you keep only the values that are non-null. And then you go through these elements, and for these elements, you need to figure out in which column they are and what is the value, of course. And this is essentially what you need to do. So you can read the code for being more clear, but essentially the point is that you have two loops, an outer loop and an inner loop, and the inner loop, we'll discuss this later, as variable bounds, because the bounds depend from what you just read here. We will have plenty of these schedule and graphical representation of what happens in time. Even if it is not indicated, the horizontal axis is, of course, time, and the colors represent the different operations. Not all operations that are here will appear on the right. It will make the schedules incredibly messy and possibly unreadable. So there are only some operations you can easily guess which ones, but sort of to give a sense of the schedule. So let's come back to us, right? So we say that there is this problem of variable latency. So imagine, for instance, that this particular access comes from a cache, right? These are different data structures, so typically they might be placed in different memories or in different areas of memory. And this one has, imagine, a cache. So this one is variable latency. It can be hit and miss. And what I said before is the natural assumption, unfortunately, for a static HLS tool is to assume the worst case. So like essentially nullifying the use of a cache, because I will in any case wait all the time of a cache. Now, notice that in this example, for instance, things are not so bad. because you can pipeline perfectly well. There are no dependencies in this loop except for the accumulation, for the fact that you are taking this temp and accumulating. So apart from here, where there is a dependency between these adds, there are no dependencies, and therefore you can do all your loads in parallel. And the fact that you have to take longer has only an impact on the individual iteration, but not on the initiation interval. You can initiate every cycle because add takes, in this hypothesis, only a cycle. So you get perfectly high throughput. You may have some cost that may not be completely visible a priori. The fact that, for instance, you have this very long pipeline, right? You may have a result that comes very early because there is a hit, but then you need to wait and keep it around until the end, until the worst case. In some cases, like floating point units or other situations, right? There may be no way of suppressing the cache. Maybe in the case of the cache, you suppress the cache, so you get the result late anyway. But maybe also in the case of a DRAM, you don't get it always at the same time. It may depend on whether the page of the DRAM is open or closed. I don't know if you are aware of these kind of details, but the point is, you need to keep things around in this extremely deep pipeline. When I'm saying extremely deep, I'm saying this because I'm seeing here cache miss, and I think as a cache miss as something that is more in the hundreds of cycles, or 100 at least of cycles, and therefore this is a very long latency to sustain and to create a pipeline for. Okay, but again, in this case, we have a high throughput. Now, this is not true if the variable latency is somewhere else, right? For instance, if it is the adder that has a variable latency. And again, now, if I have to assume worst case latency, because this is the only way I can design a schedule that is good for all seasons, whatever happens, because it's static, now I'm impacting the II. I have an adder that can do 1 to 3 cycles, but now I am always starting every 3 cycles, and I'm getting a terrible throughput, right? Because this is a throughput as if my adder were always slow, if my variable latency were always the worst possible. So what can I do? What else can I do about these variable latency components? But the other approach that one can do is to say, I assume instead of the worst case, I assume the best case. And if it is not met, I will stall everything. You may remember, I don't know if we have really said this, but this is a typical thing that we do in VLIW processors when we have cache misses. We assume that they are a hit, but then if they are a miss, we have a schedule. The schedule is static, so we have to stop everybody waiting for the load store unit that needs a result, right? Is almost the only thing that we can do. And again, because static schedules in HLS or static schedules in processors, they are essentially the same thing, the result is the same. What we can do is that we assume only one cycle for the load, then the first time we're lucky is a hit and we start the multiplication, but then I have a miss. I discover during this cycle or at the end of this cycle that it was a miss, so I'm not ready to continue. What I do is that I disable everything in my machine until I will receive the information that finally the result has come back, and then I continue whatever I was doing. I continue my schedule for iteration 3, for instance, but I also continue reactivate the pipeline, the internal pipeline of the multiplier that I had stopped. Now, one of the things to notice here is not very visible in this little period covered by this diagram, is that I am stalling everything. And when I mean stalling everything, I'm stalling also the operations that are critical to the initiation interval. One way that you can think of it is imagine that there are other iterations before, so that this is not iteration 1, but is iteration 100. So there are other iterations before. So imagine this diagonal of adds, which is the key, as we said before, to the initiation interval 1. And what we have done is that there should have been here an add, a green add, but we had stalled the complete machine, including the add. So basically, there is one add here, nothing for 3 cycles, and another add, the subsequent add 4 cycles later, which means that our iteration interval is not actually 1 anymore, but we're actually damaging by doing this. We seem to be doing better in some sense because we are now trying to react positively to the fact that some loads are hits, but in reality we are damaging the throughput, and we are damaging it by an extent that depends on how many misses there are. So it's not necessarily a great idea, but it turns out that it is a great idea, or it is a useful idea, when we apply this in the case of an operation that is on the critical path, that is critical for our iteration interval. Because now we have an iteration interval that is assumed to be 1 because we assume that add takes only 1 cycle. As soon as we see that is not the case, we only in this case lengthen the initiation interval. And so we have now an initiation interval that is anywhere between, on average, between 1 and 3, and it depends on how many times I am unlucky and I get an add that takes 3 cycles. But is certainly better than when I was assuming that it is always 3 cycles. What happens with dynamic HLS? So if I am doing a schedule that is dynamic, or in other words, if forget the HLS part of it, if I am designing a circuit that is completely elastic to the different latencies of the different components. Well, what I get is a schedule essentially like this, but you see that is not fantastic. It is, again, it has a seemingly a great schedule in the sense that I am reactive to the length of the variable latency component, which in the first case is always the load. But in reality, what you see is that we are losing cycles somewhere. And why are we losing cycles somewhere is because we have a constraint in the simple dynamic circuits that we do, essentially the one that we have seen last week or in the previous video, which consists in the fact that although we are out of order of the with respect to the different operations that are in my circuit, so the different operators do their job at the time they need, and maybe not in the program order, but in any other order that is semantically equivalent. But within a unit, we are in order. Right? Remember a bit the notion of tokens that go through our circuit. The tokens that go through a unit are never exchanged in terms of order. The first token that goes through is always the first one that comes out. The first iteration is always the first token that arrives at the end of my circuitry, which is reflected in this. Until I see the cache miss that is over, there is not a new load that starts. So I'm losing my pipeline is actually not used very well, and not used as well as in the case where I was counting on all load instructions to take 4 cycles, and therefore I could start here in a static sense the load, because I knew that it would end here and the output will be still in order. Now, if I start here a load, I'm not sure that I will maintain things in order, because maybe this load terminates before and this after, and this is not acceptable in this, if you want, simple out of order protocol or simple out of order paradigm. On other sides, things go well if it is in the case of the add, for instance, because on that side, when I'm looking at operations that are variable latency, but on the critical path of the execution, everything there goes well because I keep them in order. It's fine, but I shrink and expand them as I need. So you see that this is actually relatively similar to the stalling situation, right? Essentially, what the dynamic HLS does is not so different from the stalling the pipeline, but stalling in a more fine grain than the static, than stalling the complete machine, the complete finite state machine in the static. If we want to be a little bit more dynamic, or one way to be to create this kind of dynamism around variable latency operations, one way to handle it is to split and decouple different parts of the code. You can see this as a sort of poor man dynamic HLS, if you want. You can take this example, whatever it is, right? It reads for every iteration, reads a couple of things, adds them and stores. So it's an add of 2 vectors in a third vector. I suggest that you ignore this. This drawing is taken from one of the papers that are mentioned in the last slide. And I think the story is handled in a way that I don't find particularly clear. But the intuition is the following, is that instead of having a single loop, you split this loop in 2 parts, one part that does only the loads and one part that does everything else. And the part that does so is loop splitting, is in a sense you could say is the same loop splitting that we were describing in the part on the polyhedral, except that we are not in a situation here where we could apply the polyhedral transformations, or we will not see the importance of the polyhedral transformations. What we do here is that we have then a first circuit, completely independent, that produces values from the loads and puts them into a FIFO, and another completely static circuit that looks into the FIFO, sees if there is something, and every time that there is something, launches a new iteration or inserts something in the pipeline. So you get an execution structure that is essentially this. You have on one side the loop that creates all the accesses with these variable latencies and enqueues it, puts them into the FIFO. And from the other side, I'm showing this in a different diagram just to give the intuition that this is a different machine that insists on the same FIFO that is placed in between them, and whenever it finds something, it dequeues it and puts it through the pipeline. Now you understand that this one is a perfect static schedule, in the sense that it does always the same thing with the same latencies and so on, and has the possibility of starting something every cycle. If it doesn't start any cycle, it's because there is nothing in the queue, but as soon as there is something, it starts, right? So this circuit can be created with a normal HLS tool. As I said, if you look at what the execution gives, and if you put together these two parts in the same, you understand that is essentially the same thing as the data flow version, as the dynamic schedule that we have seen before. That's why I call it a poor man or a poor person a dynamic scheduled HLS, in the sense that you take the original code, you add this information about using the FIFO, and then whatever else is left can still be static, so you can leave it to the tool. And what we see here has been done by also the people that wrote this paper, by essentially trying to do this transformation automatically, so this code restructuring automatically, but you could do it manually, and then use standard tools, standard HLS tools to do the actual implementation. Because it is the poor person HLS, dynamic HLS, it means that it has the same disadvantage. It suffers from the fact that you are still executing in order. What one would like to do as the next level in terms of performance is something that is truly out of order. So again, not only out of order as we meant in the last lecture, by having different operators that do their respective operation at times that are not the original ones specified, or in an order that is not the one specified in the original program. That is the out of order, the extent of out of order that we did there. But a true out of order, exactly in a sense as our superscalar processors do, where we have, like here, for instance, we have the multiplications where we do in cycle 5 the first multiplication, we do in cycle 7 the third multiplication, and only in cycle 9, when the operands will be available, we'll do the second. Again, this is what we do in our processor. This is the extent of out of orderness that we absolutely support in our superscalar processors, which may be very difficult to support in general circuits. One reason why we can sort of easily do it in this case, and again, I'm not showing how the code restructuring has to be redone, but is probably not very convenient to do, but still possible. Maybe not in C. I'm not sure that I could write it in C and have a regular tool do it, but I can certainly write relatively easily this in Verilog or VHDL. But one of the key that make this easy is that I get results out of order, and the final result is what needs to be added. And I am lucky here because the addition is a commutative operation. Let's not enter the discussion of floating points and so on. Let's assume these are integers. So since it is commutative, I get results out of order, but whatever I do here for my addition is going to be fine, and therefore this is not particularly difficult. And because I can do it, what I achieve is a II of 1, right? So I completely hide the fact that some iterations are longer and some are shorter. Now, doing this in a more general sense is difficult. Why is it difficult? Because again, in this case, I can survive with these additions not done in the correct order, because this addition is commutative, but whatever else could be there could be possibilities, and there will be very often the possibility that what I find there needs some form of reordering. So what I need to do in this case is to basically associate, consider each of these iterations an independent thread. And so go through, you may see this as one of the circuits that we had, is essentially a pipeline, right? But in this pipeline, what you do is that you introduce values with an ID to know what are you introducing, and making sure that when things come out of order, you go and get the rest of the context that you may need. Essentially, what is the context here is what are you accumulating, but of course here you don't need to really know the context because you are always accumulating in any order, so you don't care. In other cases, you may care. We'll see an example a little later where I do need the context, okay? But the idea is I have here a statically scheduled component that can start things every cycle. I can give things out of order to it. They will come out even less in order than they were at the beginning, but I associate, I write somewhere all the context that goes with each piece of data, and I will put back together the result with the context, if you want, as written here, the live values of the thread. What was all the other variables that go with that piece of data, so that I can continue the computation once it comes out. Now, again, what you see here is a perfectly understandable, I think, maybe you need to think about it for a second, but a perfectly understandable computational paradigm to create circuits, but it becomes heavy to do, and you need to have buffers that may be too big to justify themselves, right? The benefit may not pay off to create these buffers, because in these buffers I need to keep and search associatively for all my my threads, right? Now, so far, we have been speaking of variable latency operations, right? We have taken these two examples of the load that misses or of the add that has a variable latency. But you have another form of variable latency, if you want, but at a bigger scale, when you take, for instance, into account the fact that here you have outer iterations, and these outer iterations are made of another loop that has a variable loop bounds. It's what I was mentioning already a few slides back. Since I don't know how many non-null elements there are in a specific row, the number of iterations that I have to do, which corresponds to the number of non-null elements in this row, is variable and depends on the data. So what happens when I execute this kind of code? We have been looking so far only to the inner loop, right? We have been focusing on this one only, right? And I do it, but I have typically elementary no way to overlap with the next one, right? I arrive here, I don't know how long this will be, so I need to finish it completely before I can start a new outer iteration. And so I have to empty the pipeline between two of these. If this, for instance, this matrix is very sparse and there are only 1, 2, 3 elements non-null for any row that has non-null elements, I end up losing a lot in terms of II between these iterations. And so the performance may be particularly poor. So what can I do about this problem? Well, it's not terribly difficult, right? If you think about it, it's the same problem that we had before. We can split these two parts. We can look at the outer iteration and split this part as an access part is exactly what it's doing, is doing loads, put these results into a FIFO, and then here do this as a separate part that depends on the loads. So split these two parts and connect them with a FIFO, and this is exactly what happens here. Instead of being shown on two halves or two independent diagram is shown on a single diagram, but here you have one of the finite state machines that produces all these loads and the other one that executes. And at this point, this one starts as soon every cycle can start something new. So when something is finished here, has a cycle empty, so it can start the second outer iteration. So the first inner iteration of the second outer iteration, right? So it works fairly well. Since this access execute decoupling that we have seen before, I say it is a bit of the poor man or poor person dynamic scheduling. If you do dynamic scheduling in the same spirit of what we have seen last week, you get exactly the same result, and maybe the advantage is that you get it without any transformation, whereas the transformation that you have to do for this access execute decoupling may be a little annoying to perform, right? Now, what happens if in all this, on top of the situation that we have just seen, we have loop carrier dependencies and long latency dependencies. That is, essentially, we have, for instance, the addition that is doesn't take only one cycle, but limits our latency by our initiation interval by having a high latency. So I'm not even looking at the variable latency. Let's assume that is simply high latency, which means that for each inner iteration, I have an initiation interval of 1. Okay, of 3. So I have a relatively poor throughput for each inner iteration. And what I can get if I do the what we have just done, I decouple the generation of the addresses, the external iterations from the rest. So if I overlap as well as I can, I do get this kind of behavior, which is good in the sense that I start immediately the first inner iteration of a new outer iteration. Okay, I start it as soon as possible, but I keep losing cycles in between inner iterations because of this dependency. And now if you look at this carefully, you can tell yourself that this is silly, right? Because here I could do an orange load with the so one of the inner iterations. I cannot do the inner iteration of the first outer iteration, but I could do an inner iteration of some other outer iteration, like the second. So I could do this one here, because this one has no data dependency, is not linked to any data dependency from the to the previous one. So this is the idea, right? This is what you would like to do, except that now you need to do, again, a completely out of order, because now you have the loads in the same unit that belongs to different outer iterations and mix in every possible way. But if you do this, you get the kind of performance that you can expect for this kind of piece of code. What you see here is, of course, so out-of-order execution is what we were discussing already before, right? The moment we were assigning these thread IDs and carrying these context. I said before, we didn't care of context because the context was just the addition, and since we can do the addition in any possible order, it doesn't matter. We don't care to know what was the state, this context. This is the same situation in the sense that we still want to reorder. These are essentially threads, each of these, right? All these inner iterations are independent threads that should be executed as soon as they can. But what is maybe interesting here and different from before is that now I do care. We need to care for the context in the additions, because this addition and this addition, which sort of are only one cycle away from each other, are not doing the same addition or the same accumulation, are doing two different accumulations. So I need to retrieve, whenever I do one of these addition, one of these green additions, I need to retrieve the partial sum that I was computing with the previous one of these green additions that may not be the previous one in terms of in temporal time, right? In cycle 8 and in cycle 7, I was doing a completely different additions, but I need to find the twin, the companion partial addition that I was using. And this is exactly what that context in that table we have seen before represents in this case. And of course, in general, it can represent anything that is the state of my computation, right? But this is an example where that context is, in fact, needed. So what we have done so far, if you think about it, is essentially at the granularity of instruction level parallelism, right? We have all these instructions, and we are trying to use a single data path as much as we can and in the most efficient way. Now, the next level is to try to extract further parallelism by trying to replicate my data path, sort of looking at multiple iterations at the same time, not only pipelining, but which is using better a single set of resources, but also having more sets of the resources to use at the same time. Of course, the first thing that comes to mind is to say, okay, that is called unrolling, right? Instead of having a body that contains one computation, I unroll, I have two bodies, and at the moment I have two bodies, I will have naturally in my circuit two copies of the circuit that operate at the same time, which is essentially true, except that it may not bring the advantage that we hope for, right? If I use the unroll factor to the pragma in HLS, like in Vivado HLS, so if I simply rewrite manually twice the body of the inner iteration, I don't necessarily achieve the advantage that I am probably expecting by doing this. What happens here in this situation is that because of the II of 1, the fact that I parallelize and I do these two operations in two different data paths doesn't help, because I would have one cycle later, I would have still the opportunity without absolutely any loss in time to do the second operation in the same data path, right? So I have exactly the same performance, but I have twice the resources, or almost twice the resources, which is a bad idea. So loop unrolling may work, but loop unrolling may also not work. And one way of looking at it is that maybe I need to do loop unrolling somewhere else. So one idea could be to say, well, instead of replicating the body of the inner loop, maybe I can replicate the body of the outer loop, which means replicating the complete inner loop, including is 4 and so on, right? Which will give more or less this kind of qualitative result. This result, if you stop the video, you can try to read it a little bit more carefully, but essentially what it does is that is unrolling out the outer loop. It's done, and it looks a bit like if it were done in Vivado. Vivado cannot, and I think any of the tools that I know cannot unroll the outer loop, so you have to do it by hand, which is what is done here, right? I'm doing there is a temp 1 and temp 2, there is a 4, there is a computation of out, there is a 4, there is a computation of I plus 1. So it's just unrolling by a factor 2 of the outer loop. But on top of that, it does, and you see here actually the syntax used by Vivado HLS for doing this decoupling between access and execution, what we have called at least access execution decoupling, which is this introducing into a FIFO what is read from memory, right? It does these loads, and the result of the load, which is this S, is put into these FIFOs, and then the FIFOs are read. And this is the way you tell to Vivado to decouple these two parts with the FIFO, so that you can have the kind of executions that we have seen before, and that corresponds to these producer-consumer situations that we have discussed before. Now, I have to admit that we have not tried this piece of code, but we are almost sure that actually Vivado HLS will not like it in this case because of the exact content of these inner loops. So it's something that you could not do probably in Vivado HLS, but certainly you could do qualitatively the same thing in VHDL or in by other means. And would it work? Of course, it would work in this case, right? It would achieve at least something better, because now these colors represent the complete set of iterations of one of these 4. So one of these 4 would operate into one of the data paths and will do whatever it needs for the time that it needs, for the number of iterations that it needs. And the second outer iteration will be going on at the same rate and at the same speed in parallel. What makes them different in length is the fact that the number of iterations of the two is not the same and is not predictable at compile time. So there is one of these two data paths that forcibly is partially unused because it finishes early but needs to wait for the next outer iteration to start, that is to move on to I3 and I4. Now imagine this situation when you are unrolling not a factor 2, but you want to have more spatial parallelism. Imagine the kind of situation where you have, I don't know, 64. These are extremely simple data paths, right? So it is reasonable to expect that you can put tens, if not hundreds of them in parallel. Imagine trying to do this. Imagine that you have enough parallelism, essentially large enough matrices to justify this level of parallelism, which is something that is reasonable, right? Imagine, for instance, that these sparse matrices are representing graphs, right? Large graphs, Facebook, Google, whatever, name it, social media, and blah and blah. They are matrices with millions of rows and columns. So it makes sense to have this parallelism extended to maybe 64, 128, 256, call them PEs, or unrolled by a factor 256. assume that. Now you can imagine that this might be a disaster. If you have a relatively high variance in what is the number of rows, you always land out of 266 on one row that has a lot of non-zero elements and has a very long execution, and maybe all the others finish in a small fraction of the time and do absolutely nothing for the rest. So this is very bad. It's something that if you look at this from the perspective of a software developer, which maybe some of you are or have done projects in that sense, what you need to do is you have to balance the load of these different threads, right? You have different threads of different lengths, and you need to schedule the threads in a more smart way. So what you need to do is to go into a all new picture, if you want, a whole new set of difficulties, which is the one of load balancing, and have essentially here some sort of distributor that is in front of all these replicated pipelines and looks at all these pipelines and see which one is free, right? These pipelines may be pipelines that have not necessarily initiation interval 1 in the sense exactly that we have seen here, right? This is one of these pipeline and is not usable for some time, but has an initiation opportunity that is there. And so this distributor looks at all these, let's call them processing elements, and when it sees that a processing element is free, dispatches a new job, right? And then there is a collector that, for instance, takes away all these things that come out completely out of order and reassociates them with the context, exactly the same leitmotif that has been coming up a few times today, that is with their state of the computation, and maybe reorders and sends it down to further stages of the computation. Now, this can be done. This is more than doable. Is done in practical cases by designers. To a large extent, I think almost nothing except some research papers can do reasonably well this in automatically, and this is a very significant design effort if you have to do this in VHDL. But this will give you the amount of parallelism that or will allow you to exploit the amount of parallelism that is intrinsic in the program if you do the right job. Okay, so it has been a longish trip through a number of the difficulties of getting a good schedule. But beyond the, let me say, almost trivial issue of compacting for a specific iteration a good a good schedule, but the more global problem of achieving a dense and high throughput schedule for complete problems. And maybe the part that is a little bit sad from one perspective is that it's maybe since the 90s that people have been looking at the difficulty or at the challenge of converting programs into high performance circuits. And if you look at it in some sense, only a little, very little part of the problem has been tackled. The fact of really creating these efficient static schedules for individual loops, but everything that goes around it that depends on perfectly practical issues like variable latency in various different forms that exist, has essentially not yet been tackled. And although we understand, I think, all reasonably well all these techniques, and we are all able to implement them if we need in RTL, modulo a very high effort, right? It's not like doing something like this is a little design project that we'll do in a week, right? Because creating all this load balancing, work stealing, all the data structures is heavy work, and then making them work at 1 gigahertz or whatever is the speed that we target is going to be extremely challenging. So all these things can be done, but there is very, very little help from HLS. Now, of course, you can read all the same thing that I say, that I call sad, and saying, what have we done in 30 years? Why didn't we manage to solve this problems that seem reasonably solvable? Well, the other perspective that you can have is the very positive one of the researcher, of saying, okay, now we have come to the time where this is really important. FPGAs are in data centers, and so maybe, I'm not saying they are, but maybe they could become the next computational substrate, like CPUs and GPUs before them, to perform efficiently highly parallel computations. How do we program? Great. We have ideas on how to do it, but we don't know how to do it automatically. This is great research opportunities for the future. I let you ponder on this. I wish you a great week. Here are some of the references from where many of the drawings and examples have been taken. I will post, I have posted, by the time you'll see this, I will have posted the papers on the web. As always, they are not sort of a compulsory read for the course, which I hope doesn't mean that nobody will ever look at them, but they may be interesting to check. Thank you very much, and again, have a nice week.